Hello ladies and gentlemen, my name is Mitchell Cornwall, and along with James Robinson, Michael Geithner, and Catherine Tchaikovsky, I am a part of Chemical Engineering 470's Team 10, also known as Don Quixote. Today we'll be highlighting our goals, design, and economic feasibility of our semester-long process design project. So let's get started with a little bit of the project information. Alright, so a new up-and-coming chemical company called Knit Lion Chemicals has proposed a methanol production plant to be built in Philadelphia, Pennsylvania along the Delaware River, and it's set to start up in April of the year 2020. So the targets and goals of this production plant are to produce 526 million pounds per year of 99.85% pure methanol, and to use 90% of the methane in our unique natural gas feed stream, which will be supplied at 80 degrees Fahrenheit and 400 psia at a rate of 20 million standard cubic feet per day. The final liquid methanol product will be stored in high volume containers and shipped in tankers along the Delaware River. So, moving right along to our process a little bit, we've split it up into 4 sections, which will be highlighted by each member of the group. I'm starting off with phase 1, which is the natural gas cleanup here. Niall will move on with phase 2, which is the pre-reformer and reformer section. Mike will move on with the methanol reactor section, and Catherine will work on the distillation and the storage sizing at the end for phase 4. So, you might be wondering why we have an entire production plant for methanol, but it turns out that methanol is a quite high demand chemical in today's day and age. Its uses are pretty widespread, just from general laboratory procedures to things such as antifreeze. And it's also a reagent for making biodiesel and common chemicals such as acetic acid and formaldehyde. And finally, it can be mixed into gasoline for fuel usage. So let's move right on to the next portion of our design, talking about each phase. So the first part of our design is the natural gas cleanup portion of our design. This is a very critical part of the design because we need to remove impurities such as elemental mercury and hydrogen sulfide from our feed stream, and they're found in large quantities in our feed stream. So they can do severe damage to materials such as heaters and compressors, and it also reduces the purity of our methanol product. So starting off with the mercury removal units, we used 2 adsorbent columns packed with sulfur-impregnated activated carbon to remove the mercury. Then moving along to the next section was the sulfur removal units, in which we used an amine absorption and regeneration unit and used monoethanolamine as our absorbent. This is just a quick overview of the design that we used, and this removes all acid gas because monoethanolamine has a high loading content for acid gas, and that was the decision behind that factor. And moving along to the next portion of the design, Niall will talk a little bit about the pre-reformer and the reformer part of our design.
Thank you, Mitchell. Again, my name is Niall Robinson, and I worked on section 2 of our methanol production process, which features the pre-reformer and reformer reactors. So in this process, after the desulfurization unit, we're converting methane and our heavy hydrocarbons into syngas, which is the intermediate between methane and methanol production. So synthesis gas is needed to produce it. So the first process is the pre-reformer, which is used to crack the heavy hydrocarbons into methane and water, and then this stream is fed into the reformer where methane is converted into synthesis gas. So the pre-reformer is pretty essential for our process because it allows us to utilize the heavy chain hydrocarbons that are in our feed. If we didn't have the pre-reformer, these hydrocarbons would go to waste and either compromise our methanol purity or require more work for us to separate it from the methanol product. So by using the pre-reformer, we can convert these heavy chain hydrocarbons into methane and then therefore into synthesis gas, so we're not wasting our feed. In the reformer, all of the methane and water is used to produce carbon dioxide, carbon monoxide, and hydrogen, which is our synthesis gas. And it was determined that the optimal temperature for the reformer would be 1500 degrees Fahrenheit, and this allowed us to get the needed specs of molar concentrations of our synthesis gas. So the reformer just features numerous tubes where the feed stream is fed through and heated, and then when it comes out at the bottom, we're having our synthesis gas production. And then after this, it goes into the PSA unit that Mike's going to talk about. So I'm going to hand it over to Mike now so he can talk to you about the third section of our unit.
Thank you, Niall, for the introduction. Now that we've seen the reforming process, I'm going to go through the third section of our methanol plant design, which is where we take the syngas from reforming and turn it into methanol. Before we can move to a reactor, though, we need to make sure that the composition of our syngas is optimized for production of methanol. This means that this ratio, which is the difference between the hydrogen and carbon dioxide concentrations divided by the sum of the carbon dioxide and carbon monoxide concentrations, is equal to 2. In our design, coming out of the reforming section, this ratio was too high, so we needed to lower it by adjusting the composition of our syngas. This is commonly done in industry by using the water-gas shift reaction, which exploits the equilibrium between these three components in water to shift toward the reactants that you need more of in order to get this desired ratio. Unfortunately, for our design, using the water-gas shift reaction would have meant adding large amounts of carbon dioxide, which became cost prohibitive and also would have had us relying on an outside source of CO2. So to avoid these problems, we chose to use pressure swing adsorption. The approach here is to remove hydrogen from our feed stream until we reach this desired ratio. This is achieved by adsorbing all the components in our feed except for hydrogen at high pressure, and then once the column is saturated, desorbing at low pressure and feeding all of those desired components to the methanol reactor. The overall system consists of two columns. One is at high pressure, adsorbing all of our desired components, while the hydrogen that is separated is fed to the reformer furnace as fuel, and any excess is sold for fuel credits at $2 per million BTU. The other column is at low pressure, desorbing all of the components that we want. And the use of two columns allows us to have continuous operation, so we're constantly adsorbing and removing hydrogen while desorbing and feeding to our methanol reactor. We actually determined that for our design, only 30% of the reformer effluent needed to be treated via PSA in order to reach the desired composition that we needed. So we split the stream with 30% going through the PSA system, and then the PSA effluent rejoined the other 70% of the reformer effluent and was fed to the methanol reactor. But before we could design our reactor, we needed to make sure that this feed stream was at the optimal conditions for our reactions to take place. We did this by examining existing conversion versus temperature data. We wanted to maximize the conversion in our reactor, so we chose to operate at the upper curve here, which is at high pressure of 1015 psi, and at the peak temperature, which is around 500 degrees Fahrenheit. We compressed our feed stream to the desired pressure and heated it before feeding it to the reactor, which would operate at these same conditions. The design that we chose was the Lurgy methanol reactor design. It's a well-established and proven method of producing methanol, and it's popular in industry because it allows for essentially isothermal operation. So with its cooling system and its shell and tube design, you can operate right at the temperature that you need to maintain the conversion that you want and have a constant concentration of methanol in your outlet. The reactions that take place are these four simultaneous reactions here, two of which produce methanol, and then one produces your side product ethanol and one your side product methylformate. This reaction system has a high exothermic heat of reaction, which the Lurgy methanol reactor is able to remove through shell side cooling. Water at the reactor pressure is fed in, and then when it's released at low pressure, it flashes to steam and can be used in other process systems. The reactor also has 258 tubes packed with catalyst. We used Catalco 51-7, where the reaction actually takes place. And the effluent from these tubes is fed to a vapor-liquid separator after cooling. All of the non-condensable components, so our gas, which is our remaining reactants, and any other vapors, are fed to a recycle so that we can take advantage of any unused reactants. There's also a purge from this recycle to eliminate the buildup of inert nitrogen gas, and this purge can also be burned for fuel credits because it will contain other components. Meanwhile, the liquid components coming off of that vapor-liquid separator, which includes your methanol and both of your side products, as well as some water, is fed to distillation so that we can purify the methanol and reach a sellable product. And Katie's going to take you through that process and our final method of purification and storage.
Hi, I'm Katie, and I'm here to talk about Section 4 of our methanol production facility, which is distillation and purification. Distillation is a purification technique that uses relative volatility between different components to separate them. For our specific case, we have two distillation columns, a refining column and a topping column. First, our components enter the topping column, which separate the light ends from the crude methanol. In the topping column, we have methanol, ethanol, methylformate, and water. The light ends are mainly comprised of ethanol and methylformate. These two components come out of the distillate, which are then recycled for fuel credits. The bottoms are made of water and methanol. These two components are then transferred to the refining column at about 20% water and 80% methanol. The refining column then separates water and methanol. Methanol comes out of the distillate at about 99.85% purity, which is our target goal. The water is then coming out of the bottoms and is transferred to a facility for wastewater treatment. Now that we've finished our design process, we can talk about the economic analysis of our plant. First, we will be talking about capital costs. Capital costs are attributed to the inner battery limit, the outer battery limit, and contingency factors. Our inner battery limit was based on the equipment that could be calculated in our Icarus program and then additionally from other bids received in previous years. This is equipment such as heat exchangers, compressors, drums, and towers. Our equipment that could be calculated from previous bids would be things like our reactors and our PSA system. For the outer battery limit, only previous bids from other years were used. This calculates things such as site development and raw material and product storage. These are based on an estimate. Our contingency factor was 20% of that total and then totaled to $390 million for our total capital costs. The other major factor in the economic analysis is our operation costs, which I will talk about now. Operating costs are comprised of utilities, raw materials, and fixed costs. As you see from our pie chart, fixed costs and utilities make up most of this category for our economic analysis. This is due to our disposal costs being lumped in with our heating and cooling utilities. As you can see from our utilities pie chart, waste disposal for mercury takes up a majority of our costs for utilities. This is due to the choice of disposal for mercury, which is activated carbon, which has a cycle limit of 2 days and needs to be replaced often. Also due to the high waste removal cost of mercury because it is a hazardous material. To lower this cost, it would be prudent to find a different natural gas feed stream that has a lower impurity ratio, just because it would be easier to design equipment that would require a lower percentage removal of mercury, and then additionally would also lower capital costs for raw materials because there would not be an activated carbon requirement to be replaced every 2 days. One of the reasons that the heating and cooling utilities makes up such a small percentage of our utilities overall is because we generate our own fuel within our plant. Our pressure swing absorption system, which removes hydrogen from our feed stream to get a desired ratio, produces pure hydrogen, and we are able to use a percentage of this pure hydrogen to heat our reformer furnace and allow our reaction to syngas to be completed. The hydrogen that is not used in this section is burned for fuel credits along with our purge stream from our recycle and our light ends stream from the distillation. Raw material costs can be mostly attributed to our feedstock. This is because our natural gas price is high compared to our catalyst cost for our plant. To lower this price overall, we would need to select a different natural gas feed stream. Fixed costs, however, are dominated by taxes and repairs and maintenance. These factors are calculated based on our capital costs, which is a percentage overall. To lower these costs, we'd have to lower our capital costs, which could be done by either of the recommendations in earlier slides of changing our feed stream or just redesigning our plant. In further economic analyses, we were able to determine our net present worth via a cash flow cycle. As seen in this graph, our net present worth never becomes positive, even though it does start to increase after our years of startup. From this recommendation, it can be made to not build the plant based on poor economic outlook. Our ATRR, or after-tax rate of return, is lower than 15% and calculated at negative 9.5%. Because this is so off from our goal, it is unlikely that this plant will succeed under current conditions. Additionally, the net present worth at the end of our 15-year life cycle was calculated to be negative $218 million. And our required netback, which is the dollar amount we'd have to sell our product for to make a profit on our current design, is 29 cents per pound of methanol produced, which is a 200% increase, over a 200% increase from our current market value of 12.5 cents per pound of methanol. Therefore, it can be recommended that making additional changes to the natural gas feed stream or redesigning the plant would be needed to continue with this study further.